Hi, welcome to section 9.1, Review of Radical Equations. Our objective is to simplify radical expressions. For homework, we're going to be working on a worksheet. The answers to this worksheet will be posted on the board tomorrow. Radical expressions are expressions with square roots. So anytime I talk about doing a radical expression, make sure you're aware of the fact that I'm not talking about like California radical, but actually dealing with square roots. Now what we're going to do with this is we're going to simplify, add, subtract, multiply, and divide with square roots. This technically is an Algebra 1 lesson, so a lot of this stuff you probably should have seen last year, but it's a good review before we move on. The first examples we're going to do are simplifying square roots, and if you notice, we have two of the exact same square roots. It's not that I didn't know it, but what I'm going to show you is two different methods for how to simplify a square root. Square roots come from the opposite of squaring. Just like plus and minus are opposite, squaring and square rooting are opposites. So the first way I'm going to show you how to do this is definitely more of an advanced skill. What you want to do is you want to look for perfect square numbers that multiply to give you 24. And not just any perfect square numbers, but the biggest perfect square number. The biggest perfect square number that we have that multiplies to give us 24 is actually 4. It's the perfect 4 times 6. Now, this square root of 24 is made up of the square root of 4 times the square root of 6. The square root of 4 is a perfect square number, it's 2. The square root of 6 is not a perfect square number, so we have to leave it. And that's our final answer. A nice easy way to double check this is going to be type into your calculator square root of 24, type into your calculator 2 square root 6, and make sure the decimals match up exactly. Now there is another method to simplifying. What we could end up doing is we can actually break this down using a prime factorization tree and look for all of the prime numbers that multiply to give us 24. So here we go. The first ones that come to mind are 2 times 12. 2 is prime, so we stop with 2, but 12 is not. 12 breaks up into 2 times 6. Again, 2 is prime, but 6 is not. It breaks up into 2 times 3. In order to have numbers that come out of a square root, we have to look for 2 of the exact same. Here's 2 of the exact same numbers, so I'm going to circle them. Now, when we do this, we only look at the prime numbers, never any of these composite numbers. Pairs of 2's, here's a 2 without a partner, here's a 3 without a partner. Now, those 2's pull out as one grouping of 2's. That 2 and 3, they don't have a partner, which means they're stuck inside. Any groupings that come out, multiply. Any numbers that are inside, multiply. And 2 times 3 is 6. We have the same answer. Either method works perfectly. It's just going to be whatever you would prefer. So for our next example, I want you to try and simplify the square root of 108. Use either method for what you would prefer, but press pause and let's see what we can do. Hopefully for your answer, you got 6 square root 3. So let's see how we got this. The method I would prefer is looking for the biggest perfect square number. Now I know I'm dating myself, but back when I was in high school learning this, the way my teacher taught me how to do this is start with the perfect square number just below the number we're dealing with. So when we think of our perfect square numbers, we're thinking 4, 9, 16, 25, anything times itself. So the biggest perfect square number that falls just below 108 is 100. See if it divides in evenly, and that obviously doesn't. So go down 1. Go to 81, it doesn't divide in evenly. Go down 1. 64. 64 doesn't go in evenly. Go down 1. Now we're down to 49, doesn't go in evenly. Go down 1. 36. When I type into my calculator 108 divided by 36, it gives me 3. So I know it does go in evenly. It's 36 times 3. I'm going to square root both of those. The square root of 36 is a perfect 6. Square root of 3 is not perfect, so it's stuck inside. Remember, we have an alternative method as well, so let me erase this. We can do a prime factorization. It just takes a little bit longer. So here we go. 108, I know for sure it's divisible by 2. It's even. It's 2 times 54. When I see 54, I know that's a multiple of 9. It's 9 times 6. Neither are prime. Now, 9 is 3 times 3, and 6 is 2 times 3. And we look for partners. Partners of 3s, partners of 2s, and then here's a 3 without a partner. He's stuck inside. Now, we have partners of 2s. They come out, but you only write one. It's the 2s. Partners of 3s. They come out as well. They're the 3s. Two things on the outside, they're going to multiply, and we have a 3 that's without a partner, so he's stuck inside. 6 root 3, either way you look at it. So the next topic that we have here is adding and subtracting with square roots. Before we start adding and subtracting with square roots, the first thing that we're going to want to do is simplify all of our square roots. We're going to want to simplify the square root of 12, the square root of 3, and the square root of 8. So let's start off with the square root of 12. For the square root of 12, I'm going to simplify it my preferred way. Remember, you can always use your prime factorization tree. 12 is going to be 4 times 3, 4 being the perfect square number. When I square root 4, it comes out as a 2. There's already an 8 outside, so it's joining something on the outside. To make 8 times 2, which is 16, the square root of 3 is stuck inside. 5 root 3, well, root 3 doesn't have any perfects that divide in evenly, so it's going to stay plus 5 root 3. And the square root of 8, it's 4 times 2. The square root of 4 is 2, the other 2 is stuck inside, minus 2 root 2. Now, when we're adding and subtracting with square roots, think of them as if they're x. So I'm going to put this in a different color and throw it all the way at the bottom. If I had a 6x, 16x, a 5x, and a minus 2y, notice like terms would combine to give me 21x. The unlike term would just tack on along at the end. Same thing happens up here. Think about the number inside the square root as our term, like an x or a y. If they're exactly the same, they're going to combine. Not change at all, but stay the square root of 3. And we can't combine with anything that's not the same. So here we go. When I combine 16 root 3 plus 5 root 3, that gives me 21 root 3. Square root of 2 is different, so minus 2 root 2. So now here's one for you to try. 5 root 18 minus 4 root 8 plus the square root of 27. Press pause, and let's see what we can do. So hopefully your first step was to simplify this. 18 breaks into the perfect square number 9 times 2. The square root of 9 is 3. It joins that 5 outside, where it becomes 15 with a root 2 left over. The square root of 8 is 4 times 2. The square root of 4 is 2. Joins that minus 4 out in front to become minus 8, and the root 2 is left over. Square root of 27 is 9 times 3. The square root of 9 is 3 with a root 3 left over. Look for our like terms, so the exact same thing underneath. Just add or subtract the numbers out in front, and 15 minus 8 is going to be 7. Leave the square root alone just like you would leave an x alone. And then we have plus 3 root 3. Our next topic, we're going to talk about multiplying square roots. So we have 5 root 6 times 3 root 8. So what we want to do here is we want to do outsides times outsides and insides times insides. So here we go. If possible, you can always simplify before you start, but I gotta be honest with you. You gotta simplify at the end so it doesn't really make a difference. So what I do is I just start multiplying. Outsides times outsides is 15. Insides times insides is 48. And then again, what we want to do is look for the biggest perfect square number that divides in evenly to 48. For me, I see that it's 16. It's 16 times 3. The square root of 16 is a 4. Joins that 15 already outside, where this simplifies to give me 60 square root 3. So now here's a multiplication example for you to try. We have 2 root 12 times 4 root 10. Let's press pause and see what you do. Okay, so for me, what I'm going to do is multiply those outside numbers. So I end up with an 8. Multiply those inside numbers, and I end up with 120. Next thing that I'm going to want to do is look for the biggest perfect square number that multiplies in and gives me 120. So I'm going to start with 100. 100 doesn't go in evenly. Move down, I have 81. Doesn't go in evenly. Move down, I got 64. Nope, don't got that either. Move all the way down the list, and what do you have as the first perfect square that divides in evenly? It's actually all the way down to the number 4. It's 4 times 30. Square root both of those. The square root of 4 is 2. That 2 is going to join that 8 outside, where it'll multiply together, ends up giving me 16 square root of 30. Our last type of examples are on dividing square roots. Now we have 2 different types of divisions here. Now, when we're dealing with square roots, we cannot have square roots on the bottom of a fraction. Square roots are allowable only on the top. Now, we have 2 different cases here, and it's actually going to require 2 different things to happen. So let's deal with this first one. We have a monomial, 6 root 6 on the bottom here. Now, the 6 out in front isn't the bad thing. What's bad is that square root of 6 on the bottom. Now, what we have here is part of our rules with fractions. We can change and alter the way a fraction looks, but whatever you do to the top, you got to do the same thing to the bottom. So what I'm going to do is I'm going to multiply both my top and bottom by the square root of 6. Whatever's inside that square root, that's what I want to multiply by. And here's what ends up happening. Tops times tops, insides times insides, and I end up with 8 times the square root of 90, bottoms times bottoms, and I have 6 square root 36. And we're going to simplify both square roots. So here we go. Square root of 90, we want to find out what the biggest perfect square root is that divides in. It's 9. It's 9 times 10. That 9, when I square root it square roots as a 3 and it joins that 8 outside to become 24 square root of 10. On the bottom, the square root of 36 is perfect. I'm going to scratch that square root of 36 out and just write down times 6. 6 times 6 is 36. And once you're done, we want to compare outside numbers or any inside numbers, and we want to reduce that. So here we go. 24 and 36, what are they both divisible by? Hopefully you said 12. So that's going to reduce down to give me 2/3. And the root 10 is still stuck on top for a final answer. Now the second one. I would love to multiply the top and bottom by root 3, just like I did for this one, but here's the problem. I have a binomial. I know whatever I'm multiplying by, it's going to need to be distributed. So if I just multiply by root 3, this square root will clear up, but unfortunately it transfers it to the other piece because it has to distribute. So instead what we're going to have to do is deal with conjugates. What a conjugate is when you have a binomial square root on the bottom. You're going to multiply by the exact same pieces, so a 6 and a root 3, but with a different sign in between it. What we're going to actually end up doing is we're going to force a difference of 2 squares to happen, where your middle terms cancel out. Now up top, we're going to distribute. 9 root 10 times 6 minus root 3 is going to give me 54 root 10, outsides times outsides, smack on the inside, minus 9 square root 30. On the bottom, we're multiplying 2 binomials, so I'm going to have to FOIL. When I FOIL these binomials out, I end up with 36 minus 6 root 3 plus 6 root 3 minus the square root of 9. We want to clean this up. Up top here, we want to think, is there any good perfect square numbers that divide in, make us 30? There's not. Same thing with 10. That's as simplified as it gets. On the bottom, let's simplify this. Negative 6 root 3 plus 6 root 3. We got the same in sides, which means they're like terms. We can combine them. Negative 6 plus 6 is 0, and they cancel out. And the square root of 9 is 3. Scratch it out and write a 3 instead. My top we're going to keep 54 square root of 10 minus 9 square root of 30. And on the bottom, 36 minus 3 is 33. Now, the last thing we want to do, we have just a regular whole number on the bottom here. what we want to do is we want to look at each and every piece. On top there's two pieces, it's a binomial, and the bottom only one piece of monomial. We want to look at all those outside numbers and see if they're all reducible by anything. And when I compare 54, 9, and 33, I see that they're all divisible by 3. So let's do that. We're going to do 54 divided by 3, 9 divided by 3, and 33 divisible by 3. What that ends up giving me, make a little arrow here, it gives me 18 root 10 minus 3 root 30 all over 11. Okay, here's two examples for you to try. Again, press pause and let's see what you can do. Okay, so here's what I would do. I would actually start off right here. I'm going to reduce this. So I'm going to show a slightly different way of doing this. 14 divided by 6, they're both divisible by 2. That's going to give me 7/3. I'm also going to reduce my inside numbers as well. Outsides reduce with outsides. Insides can reduce with insides. Insides are also going to be divisible by 3. When I do that, 18 divided by 3 is 6, and 15 divided by 3 is 5. Still have that nasty square root at the bottom. Now, although this was unnecessary, 18 times 15 is one ginormous number that I really didn't want to deal with. So what I'm going to do is multiply now in the reduced form, timesing the top and bottom by 5. That's going to end up giving me 7 square root 30 over 3 square root 25. Now, square root of 30 doesn't simplify, square root of 25 does. I'm going to scratch it off and write down times 5, which ends up giving me 7 square root 30 over 15. Now we're going to compare just those outside numbers. Outsides only mix with outsides, insides with other insides. 7 and 15, they don't reduce at all. Final answer. For my last example, we have a conjugate. So if you didn't press pause and try it, let's do that now. Here's what I would have done. Multiply both the top and bottom by the same pieces on the bottom, but with a different sign in the middle. 8 plus the square root of 3. Top, let's distribute. I end up with 16 square root 6 plus 2 square root 18 divided by, let's FOIL out that bottom, 64 plus 8 root 3 minus 8 root 3 minus the square root of 9, and let's simplify. 18, the perfect square 9 times 2. Square root of 9 is going to be 3, it joins that 2 outside. I get 16 square root 6 plus 6 root 2. On the bottom, 8 root 3 minus 8 root 3, they cancel each other out, and the square root of 9 is 3. On the bottom, 64 minus 3 is 61, and again I compare my outside numbers. 16, 6, and 61. What are they all divisible by? Absolutely nothing, which means I am done. If you have any questions about any of this stuff, please make sure you bring it to class tomorrow. Tomorrow we're going to be working on a worksheet in class, just to make sure that we understand these concepts. And as always, have a good one.